Hey everyone, welcome to BCP Med. In this video, we're going to be taking a look at the resonance structures that form when a lone pair, also known as a donor group, is adjacent to a pi system. We're going to be looking at how lone pairs can delocalize into a pi system, what kinds of orbital interactions and orbital characters are associated with a lone pair, some examples, and we're going to look also at how this impacts the property of the overall molecule. Let's go ahead and get started. So when a lone pair is adjacent to a pi system, it has some properties that are somewhat different than a lone pair that's on a typical atom. Specifically, a lone pair that's adjacent to a double bond is going to be located in a p orbital, an unhybridized p orbital, as opposed to a hybridized atomic orbital such as an sp2 or an sp3 type orbital, right? This way, that lone pair that is located in a p orbital is able to be parallel to and delocalize with the pi system, which is itself formed of p orbitals, not hybridized atomic orbitals. So, for example, if we look at this molecule, which has an amine group, a nitrogen with a lone pair adjacent to a double bond, that lone pair is not going to be in an sp3 type orbital, even though if you were going to look at this nitrogen, you might see, oh, well, it has 4 electron domains, 2 hydrogens, a sigma bond, and the lone pair, and think, oh, it's tetrahedral sp3. That is actually not the case. This lone pair is located in a p orbital, right? And if you were to look at the orbital picture, it would look like this. The p orbital contains the lone pair, and it is going to be parallel to the pi system of the carbon-carbon bond, which is represented by the orbital there, that sort of diffuse arching structure over the 2 carbons. That is the pi molecular orbital. If we were to go ahead and try to draw the resonance structure for this, what would it look like? Well, we would take this lone pair, and we would use an electron pushing arrow to show it forming a new bond. So the nitrogen lone pair would actually push down into this bond here and kick this pi bond onto the carbon. From an orbital perspective, what that means is that this p orbital here with the lone pair, let me draw that a little bit better, this p orbital here with the lone pair, because it's parallel to the pi orbital, which is going to attack this pi bond. Now it's important to remember that the pi bond itself is really made of 2 p orbitals that are sideways overlapping. So what's happening is that the nitrogen p orbital is going to attack the p orbital of the carbon that's next to it, and it is going to form its own sideways overlap with that p orbital. In the process, it is going to cleave that pi bond in half. It's going to split it down the middle into its constituent orbitals and push the electrons from that pi bond into the p orbital of this carbon, right? So we're breaking the existing pi bond with the nitrogen p orbital to form a new pi bond and a new lone pair in a p orbital. So structurally, what that looks like is this, right? The nitrogen now has a double bond to that carbon formed when this lone pair on the left enters that bond, which gives the nitrogen a formal positive charge, and the bond that existed here is now being pushed completely onto this carbon as a lone pair and a formal negative charge. From an orbital picture, what that looks like is a new pi bond between the nitrogen and this carbon, and a new p orbital, or rather a split pi bond into a p orbital here with the lone pair, right? So just as we described earlier, the nitrogen lone pair attacked the p orbital of this carbon and split the pi bond, forming a new pi bond here and kicking the electron density of the double bond up into the p orbital of the right-hand carbon, right? So once again, just to summarize what we've talked about, let's walk through this one more time. Right, the nitrogen p orbital attacks this pi bond. Because the pi bond is made of these 2 p orbitals that are interacting, the nitrogen p orbital will form a new bond with this p orbital, and in the process cleave this pi bond down the middle, forcing the electron density into this p orbital, which gives you the following orbital picture on the right. So let's go ahead and take a look at some examples of larger pi systems, or lone pairs being donated into larger resonance structures. So in this case, we have the molecule aniline, which is going to have a nitrogen lone pair adjacent to a benzene ring, a conjugated pi system. As usual, or as we saw before, this lone pair, being adjacent to a double bond, is going to be in a p orbital, not an sp3 orbital. And so it is able to actually go ahead and push the p orbital and form a new bond as such. The lone pair will form a new nitrogen-carbon bond and kick up the adjacent double bond. That will form this resonance structure, where now the lone pair, or rather the formal negative charge, resides on this carbon, right? And the nitrogen, now being formally positive, has a double bond to its carbon. However, just as it occurred with the nitrogen, this carbon lone pair and the negative charge associated with it can kick to the adjacent sigma bond, or to the adjacent single bond, making a double bond, and forcing the nearby pi bond into a new carbon. That provides this resonance structure here, where the negative charge is now localized on that carbon, right? We're just splitting those, we're using those lone pairs in p orbitals to split up the adjacent pi bonds by forming new pi bonds. So this carbon had a p orbital with the lone pair, right? So I can go ahead and show the lone pair in a carbon p orbital, and that is going to attack this bond, which itself has two p orbitals. We're specifically going to attack this p orbital and form a new double bond and split the electron density into this p orbital, which is now carrying a negative charge. We can do this once more, where the electrons can kick into that bond and then onto this carbon to give this resonance structure here, where the electron density is now localized on that carbon. All of these together combine to form the superposition that is the aniline molecule. We'll talk a little bit later about how the sum of these properties influences molecular character. For now, let's go ahead and look at another example with a different heteroatom, oxygen. The furan molecule looks very similar to aniline in the sense that it has a lone pair adjacent to some pi bonds in a cyclic system. However, in this case, we have two lone pairs, and the oxygen atom is a weaker donor than nitrogen. It doesn't like to give up its lone pairs as much because it's more electronegative, but it can still do it. It can still delocalize its electrons, right? So one of these pairs is going to be in a p orbital, such that it can interact with the rest of the pi system, right? So let's say the one on the left is going to be in a p orbital. The one on the right is actually not in a p orbital. It's going to be in an sp2 orbital, because only one pair of electrons from each heteroatom will typically be interacting in a pi system. The other will be perpendicular and not interacting. We'll come back to that. But let's just go ahead and look at how this arrow pushing would work. So we can go ahead and take this lone pair and push it into that bond and kick up the adjacent pi bond to give this resonance structure. Again, then we can have this lone pair kick there and follow the chain of electrons, kicking up the subsequent pi bond into this carbon, giving us this resonance structure. Notice we're only moving two sets of bonds at a time. We're forming and breaking, forming and breaking. The oxygen is staying with a formal positive charge throughout these structures. So again, we can now take this negative charge and bring it into this bond here, and then break this bond, giving this carbon a negative charge, and that would look like that, this resonance structure here, right? Once again, we can do one more arrow pushing. This bond can, this negative charge can go there and kick the bond onto this carbon and give us the following resonance structure. What is unique about all of these resonance structures is the way that they sum together to give properties for the overall molecule. So if I go ahead and erase these arrows that I've drawn here, I'm going to show you something pretty interesting, right? So because the resonance structures that arise from this donation are formally charged, right? The nitrogens are carrying formal positives in all of the resonance structures, and these three carbons are negative. The overall aniline molecule is going to have some partial charges associated with it. Specifically, the nitrogen is actually going to carry a partial positive charge, and the carbons at these positions specifically are going to carry formal negative or partial negative charges, They're actually going to be more negative than these carbons, right? Even though they are part of the same benzene ring, the circled carbons are more negative due to the fact that the resonance structures have negative character. The same is true for the furan ring below it, right? Because all four carbons have resonance structures associated with them that place a negative charge on that carbon, all four carbons are going to carry partial negative charges in the overall molecule. On the other hand, because oxygen carries a formal positive charge in so many structures, the oxygen, which we typically think of as quite electronegative, is actually going to carry a partial positive charge. So all of these resonance structures that arise from electron donation, what happens is that a donor atom is considered a donor because it pushes electron density onto nearby atoms. It donates electron density, itself losing electron density. So when a heteroatom, a donor atom like nitrogen or oxygen, donates into a pi system, donates its lone pair, it is going to force partial negative charges onto nearby carbons or nearby other heteroatoms, and itself adopt a partial positive charge. So rather quickly, I want to go ahead and look at the significance of lone pair resonance, why it's unique compared to typical double bond resonance that you see just between carbons. So unlike carbon-only structures, those that involve a heteroatom lone pair are often significantly more contributing to the overall structure. The reason is that it typically retains full octets on all of the atoms that are involved. It's even better if we can donate into a group like a carbonyl or a double bonded oxygen that is receptive to electron density. And we'll talk about more about withdrawing groups in another video, but let's go ahead and look at this structure for the amide functional group. So in this case, we have a nitrogen with a lone pair that is adjacent to a double bond, in this case a double bonded oxygen. Oxygen really likes electrons, it's very electronegative, and nitrogen, in this case, being a lone pair adjacent to a double bond, is a donor atom. It is willing to give up electrons. And so we can go ahead and say that this electron pair can push into this bond and push the pi electron density onto the oxygen. That'll give us the following resonance structure, where nitrogen is now formally positive and oxygen is formally negative. Unlike a lot of the charged structures we saw when we looked at carbon bonds, or carbon pi bonds, this structure has a full octet on all of the atoms. And we also have negative charge placement on the atom that best occupies it, the negative oxygen. And so this resonance structure that results from the nitrogen donation is going to be very significant. It's actually going to contribute quite a bit to the overall structure of the molecule. And that impacts two main things. The first is going to be the fact that the molecule is going to carry significant partial charges. The second is that double bond and single bond character is going to change as a result of the resonance structure. So let's look at the superposition for this molecule. As you can see, I've drawn dotted lines in for some of the bonds. Why is that? Well, if we look at the two structures on the left, we see that one of them has a single bond for nitrogen and the other has a double bond. Because both of these structures are contributing, in reality what we're going to get is a 1.5 bond, which we see here, right? So this nitrogen-carbon bond is stronger than typical NC bonds that are single bonds, but slightly weaker than a double bond. On the other hand, we have one structure that has a CO double bond versus a CO single bond. And so as a result, the overall structure is going to have a CO 1.5 bond. The overall bond between these atoms is a superposition. It's a sum or a mix of each of the individual resonance structures. And because both of these structures contribute appreciably to the structure, this structure actually has significant character of both bonds. It's not almost completely double or almost completely single, it's somewhere in between. Also, because the resonance structure with formal charges does contribute significantly, the nitrogen and the oxygen are going to carry significant charges. Specifically, the N will be partial positive and the O will be partially negative because of it. Last but certainly not least, I want to go ahead and talk about what are known as orthogonal electron pairs. So for a lone pair to be in resonance with the rest of the adjacent pi system, it needs to be in a p orbital that is parallel to the other p orbitals. However, when we looked at the molecule furan, which looks like this, right, we said that only one of those lone pairs is actually going to be delocalized into the other bonds. The other one is not. Why is that? Well, it turns out that if a electron pair is orthogonal, right, if it's in an orbital that is perpendicular to the pi system, it can't delocalize, right? So if you have a p orbital, let me draw that a little bit better, a p orbital and another p orbital that are perpendicular, these do not interact. They do not form a pi bond. And so a lone pair here in this p orbital cannot interact with a p orbital that's perpendicular to it. So you typically see this, right, in a neutral atom with a lone pair that's already double bonded to something. Right? So if you have a neutral atom, like a nitrogen or an oxygen, that has a lone pair, but it's already double bonded, that lone pair will not be interacting with the rest of the system. A good example of that is the molecule pyridine. Pyridine has a nitrogen with a lone pair there. It is also double bonded, right? It has a double bond to this carbon, and specifically it's part of an aromatic ring. So if we were to look at the orbital picture for this nitrogen, we would see that one electron from the nitrogen is in a p orbital, which is parallel to the rest of the pi system. All of these p orbitals, all 6 of them, are going to be interacting through resonance. There's going to be partial double bond character between all of these orbitals, right? However, the lone pair is in an sp2 orbital. It is not parallel to the other p orbitals, it is perpendicular, and so it cannot interact with the rest of the ring. The superposition would look like this. There is a circular electron density over the ring, and that lone pair juts out completely by itself, not interacting with the rest of the ring. And that leads to some really interesting effects when it comes to basicity and acidity of molecules, specifically the basicity of nitrogens that are sp2 hybridized. And with that, we've actually reached the end of the content for this video. Thank you guys so much for watching, and if you like what you saw, please like and subscribe to the channel. To learn more, check out our other videos in the chemistry playlists, and if you're looking to branch out, check out our other science playlists as well. See you next time.